Hello and welcome back. Let's go ahead and do the next tutorial. Myself, Dr. Mantesh. We are doing this tutorial series for VLSI laboratory. Last tutorial we did CMOS inverter, that is 5th A. Let's go ahead and do 6th one, that is 2 input. So read the specification clear. 2 input CMOS NAND gate having similar delay as that of the CMOS inverter computed in the experiment above, that is this one. That means what is the delay of it? It is nearly rise time and fall time nearly equals to, both are equal. So in that case you know about these designs. However, I would at this point there is no much room for me to discuss about the theory. Let's go ahead and do the schematic of NAND 2 input NAND gate. You can flip it. So we are doing 120 nanometer technology, foundry. You can go on connecting. So there is a formula called R by K and R by 2K. R by 2R by K for PMOS. If you refer Neil West, CMOS design by Neil West, you will understand these things, and these are already there in the syllabus. So the impedance of NMOS is R by K, impedance of PMOS is 2R by K. Suppose if you want to get equal rise and fall, these two are parallel, so any one resistance will be considered. So 2R by K must be equals to R. Okay. So 2R by K, the design is there already in your syllabus. Just read it. 2R by K equals to R since it is parallel. So K equals to, that is the unit width equals to 2. Here these are in series. So I must add these two. For NMOS it is R by K plus R by K, because they will come in series, equals to R, and R by K plus R by K is 2R by K. Therefore 2R by K equals to R. So what is it? K equals to 2. Suppose if it is 3 input, R by K plus R by K plus R by K equal, that must be equals to R. So K will be 3 in that case. So let's have this design and keep this in mind, why we are taking 2 times the minimum. So here minimum is 2 micron. So here minimum is 1 micron, I have to make it 2 micron. However, it is not going to affect much in the simulation of D schematic, DSCH. It will be useful in the layout, so it is just for reference I am giving the, okay. So this also can be flipped for easy understanding. Okay. unwanted wires can be deleted using this gun symbol. That's the delete. Next thing, I want to complete the connection. Okay, let's go ahead and do. So these are 3 input MOS CMOS, 3 input MOS transistors. The fourth terminal is by default connected to the source. For PMOS it is VDD, for NMOS it is ground. So there are 2 inputs now, A and B. Another clock I would like to take and flip it. And one more thing, I want to connect it to output. This is output visible node. VDD I want to connect. That's it. Let's go ahead and check electrical connection. If there are anything wrong, it will show it for us. So I think everything is connected to everything. Let me run it. Okay, and do check the simulation. Since it is NAND gate, if any one of the input or both of the input are low, then the output is high. When both inputs are high, then the output would be low. So we are getting the output, and unfortunately we are unable to find the delay here, which is possible in cadence and all those things. Next one, we would like to do the simulation in the microwind. We have to do the layout for it. The simplest one is to go for transistorized one. We'll take simple transistor. The minimum is to 6.6, minimum width is 0.3 micron. Now by default it is taking 0.6. So PMOS, initially there are 2 ways to do it. So at this point I am doing easiest one. So you take 2 transistor, 2 PMOS transistor. You can keep side by side. Nothing wrong in it. I am not connecting. Okay. So this also works. Nothing wrong in it. Similar to that, I have to take NMOS. I have already decided this must be twice the size of the minimum. Okay, I have to move it such that I can connect it easily with gates, and gate I would like to short. Okay, I think it is moved a bit. I think still not possible. Okay, it must come in this way. So let's do this. Okay, just check for DRC. If there are any errors, it will show. Then one more. This is 2 times. Just keep this in mind. It is 2 times already. 2 times the minimum width. So what we have desired is 2 times the minimum width. Okay. Generate device. Keep it and move it. Okay, I think I came a bit out. undo, move, fine. Now I can connect. Can you see the gates are connected? The both gates here they are connected. So in that case I must also connect these things. So I am done with gate connection. Next thing, I am supposed to connect VDD. Okay, so we'll make a VDD rail better. Anyhow, this is also okay, nothing wrong in it, but edit, undo. So what can be done? These two can be shorted, which is the easiest one. Okay, in that case these two will make VDD. Okay, these two can make VDD and one can make output. So let's do this. I don't want this to be at the output side. Okay. So I'll connect these two. Stretch it. And then I want a VDD rail here. Okay. Take metal one, draw this box. And then connect these two. So now the connection is almost done for PMOS network. We'll try to do the same thing for NMOS. This thing must be, okay, let's try this as an output. I will take it to the output. Meanwhile, you keep checking for DRCs. If there are any DRC error, you should be able to see it. Check for DRC error every time. So this is a bit extra, but it's okay at this point. I don't mind in okay, this is VSS, this is VDD for you. This one is also VDD for NWEL network. NWEL, you should have a VDD. So this is bit extra now. So these two are in series, so just connect and leave it. You don't have to, okay, just look for any DRC error. Okay, now the connection is over. I have to give inputs and output. So this is, let me tell you the connection. At this point, so source and source are connected to VDD. Drain and drain connected to output. Source and source connected to VDD. Drain and drain connected to output. Now I made a mistake there. Can you see? Edit, undo, DRC, fit. Okay, this is output, so visible node is output. NAND out. Okay, so this is output. I've given supplies wherever required. So this is in series, so you don't need any connection for these two. Next thing, I would like to give inputs. Okay, inputs A and B. A and B are inputs. So now inputs and outputs are ready. If I simply simulate it, just save it. Sometimes it is not going to save. If you simply hit save, you better save as and you save it in the particular location and simply run the simulation. Okay, 0 0 1 0 1 1 1 0 1 1 and 1 0. So also what they are expecting you to write in the curriculum mentioned is time delay for all possible combinations of input vector. I think we may not be able to catch all the possible combinations, but we are getting from high to low, low to high. These are theory aspect, like one transistor is on already. Suppose this is on and next time you're trying to turn it on, it will fall and the delay would be less. If both are going to high at a time, then the delay will be very less. If any one of the transistor is trying to pull up the output, the delay is more. If both are trying to, both PMOS transistor trying to turn on, that is both 1 the delay would be very less. These are possible combinations. Already you did it in the theory part, so I don't want to take it to that point. So I just ask you to note down, because I am unable to force. There are no options like giving push button or something like this. Here we have only clock. Okay, so their pulse is also there, but I don't know whether it works or not. So at this point we are simply going for clock and do the simulation and note down the TPH and TPL. For example, low to high, it is about 4 picosecond, and here it is high to low, it is 4 picosecond. So it is some combinations you can get it, and you write it in the tabular column what I have shown in the, similar to that of what I have shown in the previous tutorial. So we are getting output, we are verified about the functionality. What I am interested to teach you about having a common diffusion. Okay, let's go ahead and take new. I would like to save it, but at this point it's okay. See, it didn't take. There are some versions, for example this version what I am using is, it's not saving it properly. So there are flaws in this, so don't worry, and just I am trying to demonstrate it. So the second way of doing the layout is you simply go ahead and take 2 fingers. Instead of 1, you take 2, generate device, same with NMOS, and now try to adjust. Okay, just check for DRC, renew violations, connect the gates, and then we have it for this one, and this is not required for us. Even if you delete it, it's okay, but anyhow it is there, let it be there, or you can delete it, nothing wrong if you delete it. Okay. what I am asking you to delete this metal, nothing wrong even if you delete it. Next one, give a ground. Next thing, stretch the unwanted thing. Now try to connect it with I'm not stretching, I have to draw it, so I have to take metal 1 and try to connect it here. So just check for DRCs every time. Also I need a VDD rail here, so one extra lambda I have extended. Those things must be avoided to save the area. Okay, and then give inputs A, second input is B, the output visible node is this, NAND out, or simply you mention out. So that's it. It's so simple. If you use common diffusion, I have used common diffusion here and even in NVEL. NVEL is common. Now even N diffusion is also common. A bit of metal is extra here. You can delete it afterwards. Let's go ahead and run. See, it is also working. It is better. The delays are less. You can note down this and you can follow this one. Nothing wrong in it. What you should do is you should say save as common diffusion. Better not to give any spaces in between. So you should give save as and then it will be saved with this name. So this is how you can able to create it. So what is there in the next part of the experiment is you try to increase the driving strength by 2x and 4x and tabulate the results. What results? They are asking you to find out the delay TPHL and TPLH, what I was showing in the simulation. However, you may not be able to get for all combinations. In cadence it is possible to force the vector 0, 1s and 0s and we can able to get all possible combinations. How to increase the strength? I'll show for any one, say for example 2x. Now say this is minimum and we would like to go for 2 times of this, say new. That means instead of 0.6 you should go for 1.2 PMOS. Okay, now you would have observed the delays. Now let's increase the strength and see the delay. Now you will have clear picture about what they are trying to do with this experiment. Let's minimize it, stretch it, that is move. So I am unable to move. So I'll try to keep it here somewhere very close to this. And let's check for DRCs if there are any violations. Same thing, I am just increasing the drive capacity, that is increasing the size, and we are trying to connect these things. Anyhow, this is not required. Even if you delete it, it works. And this is not required, but what is required is this one. Let's go ahead and draw this for output. Look for DRCs. Yes, there is a violation. Stretch it properly. Okay. Wave wall. No, we are trying to stretch this one. Suppose I intentionally making on violations, it should give, okay, nothing wrong in it. If I reduce or if I try to keep it somewhere here, it will show error. So just make everything right. Give ground, give VDD to NL, give VDD to PMOS network, and take output visible node here. Say at this point I'll take out, give two inputs A and B, that's it, you are ready to go. Now if you remember the delays what we have got, it is much more less than that because we just increased the drive strength. Okay, earlier it was showing 4 picosecond, 3 picosecond or something like that. Now it has been decreased. Even you can able to get these things just by giving proper this one, but it's okay. Fine. So just do this one. Similar to that, you have to do it for 4 times. How to get 4 times? So I'll show a bit of it. So you increase it by another twofold, that is 2.4. Sorry, I think it is already 4 times now. Minimum is okay, minimum is 0.6 now because it is 2R by K, so I should go for 2.4. Now we can increase it for 3 or 4 folds fingers and to get the optimum area, and then you can connect. So this is A and A, this is B and B. You should be able to connect it properly. Okay. So this is about 4 by 4. Suppose if you get confusion, you just keep it 2 fingers. Nothing wrong in it. So hope you understood what we are trying to do. So at this point, this video is already extending more than 15 minutes. Yeah, it's 30 minutes. So let's stop it and stick to these two.